Thank you for being here. Yep. I am grateful to be here and be able to talk with you about this. This was a very interesting exploration. There were a couple of white papers that were printed at the end of last year where multiple security agencies from around the world got together and made some very interesting statements. And we're going to take a look at those and how they apply in our sphere. So here's one of the statements that they made. I find it particularly interesting given that not long after this was published, there may have been some sort of security software update that may have caused some issues on some operating systems. I don't know. You may have seen it, you may not have noticed it. Not sure. But as these things proliferate, they themselves can become a problem, okay? And so if we can make more secure products, then the need for security products is decreased. And that's what they're calling for. They're not suggesting that it might be a good idea. These security agencies from around the world, national security agencies, are saying this must happen. All right, so in one of these articles, they talked about safe by design software. And I don't know if you can see that. Doesn't look like you can. So I will read it to you, not to insult your intelligence, but so that you can see what it says. Secure by design products are built in a way that reasonably protects against malicious cyber actors successfully gaining access to devices, data, and connected infrastructure. So this is their definition, the security agency's definition of what secure by design means. They have another definition, which is secure by default. And that one they list as secure by default products are resilient against prevalent exploitation techniques out of the box without added change. Okay, so by default, this product will be secure. We decided to expand that definition from generic product to language. And so we define language this way. Languages are secure by default if they are created in a way that protects against the production of all types of common vulnerabilities and exposures. Okay, so shifting it from being a product down to the language level. If the language doesn't let you do it, if the language doesn't let you do it, then your product will be secure by default. So in one of the other articles of these two, they make a call and they state that C-suite executives and companies must become responsible for the security of their software. Until that happens, software is not going to get more secure. Okay? So there must be some sort of impetus for this to happen. So they go over, they declare several languages as being safe. And this is the list of languages they give. Again, it's probably hard to read because of the smallness on the screen. So they listed Ruby, C#, Go, Java, Python, and Swift. There may be some missing, as you have noticed. So we went ahead and added Erlang and Elixir to this. They seemed very much to fall within the definitions that they were using for these MSLs. However, declaring a language as being memory safe is necessary but insufficient. Because if you look at any of these languages, you can either write or load unsafe code. In some of them, it's really easy to do. And so what we did is we came up with a new term, unsafe impedance. In other words, how hard is it to write unsafe code in these memory safe languages? Okay? And again, you probably can't read that, so I'll read it for you. Unsafe impedance is a rating indicating how hard it is to write unsafe code in the language or load unsafe code from libraries. Because either way, you're going to get problems. Okay, so, and again, too small to read. So we categorized or broke this into categories. So there's no unsafe impedance is one of our categories. So there is nothing getting in your way of shooting yourself in the foot and the head at the same time. You can just blast everything and be absolutely insecure. Nobody's going to stop you. And then the next one is languages that have few syntactical or other impediments to writing unsafe code, we define as having low unsafe impedance. So if you can do it, but there's a few things in your way, then it's low. Languages that have many syntactical or other impediments to writing unsafe code, we define as having high unsafe impedance. And then if you can't do it at all, we define that as infinite unsafe impedance. Okay. So that's the way we started to categorize these languages. And we also tended to move these common vulnerabilities as they're currently tracked, which are at a product level down to a language level. So these are the root causes of those. So we decided to call those vulnerabilities and exposures at a language level. And again, we're dealing in these articles with just memory, so that's what we're dealing with here. And you won't find any surprises in there, I'm sure. So here's how we ended up categorizing these. You can see C, C++, and C#, C++ and C# are unsecure by default, and they have no unsafe impedance. It is just so easy to write unsafe code in those languages. In fact, about 3 years ago, the United States Department of Commerce published a white paper saying C and C++ should never be used unless there is no other option. So there we are. Some of those may be a little surprising to some of us. You know, Rust is a secure language, right? And yet we've categorized it as unsecure by default. Well, if you look at Rust code, it's really easy to write unsafe code. You just say unsafe and you go do it. And it doesn't add any safety to write unsafe around it. There's nothing in the compiler saying, ooh, we better segment this off. Or no, it's just a flag for the compiler to tell it to ignore what you're going to be doing for, you know, don't apply any safety rules now. And so it's just incredibly easy. Now, if you compare that with something like Erlang or Elixir, if you're going to write unsafe code for Erlang and Elixir, what you really have to do is you have to load a library. And there hasn't been a ton of stuff done to make the loading of libraries easier for people who know Erlang. You get this C file, and it's got all this gobbledygook in it from an Erlanger perspective, and magic happens, and then the library is being executed and called. If you know both languages, it's easier. But strictly, if you just know Erlang, it's going to be tricky. It's going to be tricky. So that's why we have it in the high impedance, but it's at the lower end of high impedance. Both Erlang and Elixir, all of the Beam languages are. Okay, so what are we going to do? So we make a couple of suggestions. The first one is that we have a thing called a UAP, which we define as being an unsafe acceptance process. So this is going to be a business process that the business has to follow. Now, there are badnesses about business processes. There will always be a reason not to follow it. Oh, it's going to take too long. Oh, it's safe. Or some management thing comes along and suddenly we toss it all out. Business processes are difficult to enforce. Okay? And this is why we have that call for C-suite people to be responsible for security so they can enforce these types of things. Okay? So for Erlang and Elixir, and again, it's too small to read there, so let me see if I can get this lifted up. We propose any UAP must include a required measurable proof that only a NIF can solve the problem presented. We propose that this proof should include at least these items in a proposal to include a NIF in an application. 1, a statement that by the lack of a NIF implementation, one or more existing consumers, users of the software are being damaged and how. And that could be an internal user, that could be some large user outside the system, it could be any user. 2, a statement of the security risks any NIF brings, along with a statement of the potential security risk posed by the NIF's code. 3, the source code for the proposed NIF. 4, source code for unit tests when unit testing is possible, or other extensive proofs that the NIF exhibits no unsafe behavior for all conceivable edge cases. 5, measured speed increases presented by using the NIF. And 6, an alternative solution, if possible, in Erlang or Elixir that improves on the current solution but is insufficient. Now, again, the idea behind this is this should be really hard to do. If you want to increase the impedance, this has to be difficult. If it's easy to do, we've accomplished nothing. And so there are things that we're suggesting here that are very difficult to pull off because it's supposed to be that way. Otherwise, it's just too easy to make these kinds of mistakes. And then here's some nitty-gritty that us computer sciencey people need to think about. Secure by default and an infinite unsafe impedance should be the goal of every language creator and maintainer. Business practices such as UAPs cannot guarantee code safety, only reduce the probability that unsafe code exists in any software product. So, what does that mean for us? If we are buying into this, then suddenly we're in a situation where loading libraries in the beam is not a good thing. And yes, that causes some issues. That can cause some big rewrites of certain things that we all love because they're loaded as NIFs. Now, we propose that it is a worthwhile task. If we really want a language to be secure by default, we have to make it secure by default. And that means it's going to have infinite unsafe impedance as well. Infinite unsafe impedance is a target and a goal. Anything that's infinite is impossible. However, we can have very high unsafe impedance and achieve something that's reasonable and realistic. So, temporary measure, the UAFs, long-term goal.
So what is your to-do list for making Elixir and the Erlang to evolve towards higher impedance?
I don't have a huge amount of power in the Erlang community. I can't just, I'm not. But if I was king of the world, I would probably start a process to produce something named something along the lines of iron beam, which would be a beam that cannot load anything. And then I might have some other considerations after that where I could possibly make something that would make it even better. So more careful implementations down inside the beam as well.
I'm just thinking of the large systems that I've worked with over the years. Now, I think every one of them has been programmed not in one language, but in a number of different languages. If I think of React, for example, that used LevelDB as a back end. And that's not just because C was faster than Erlang for that, but because there was a well-maintained open source component that, of course, they wanted to use, rather than, building everything from scratch, which isn't necessarily going to result in a better, more secure product. So how would you advise people who need to use multiple languages in one system?
Each language, assuming they're not like C and C#, where you can just wander off into the weeds and do whatever you want, should have some sort of this acceptance process, this unsafe acceptance process. So that's our temporary solution to these sorts of situations. The long-term solution is either modify the languages that currently exist to increase their unsafe impedance, or create new languages from the get-go that have high unsafe impedance.
This reminds me of the certification requirements for aerospace software, where there are a whole lot of requirements on how the testing is done, for example. So you can imagine that something like that might become part of the unsafe acceptance process, except that those processes increase the cost of the software by about an order of magnitude. And it's difficult, really, to see how open source developers in particular will do that in the absence of resources.
Yes, and we agree 100%. This is why we need to move it to a language level rather than a business process level, because then that cost is not there. We don't have the same sort of cost structure. We will have a little different cost structure, but the question becomes, how much is software that is safe worth, considering how many billions were lost in just this recent experience that we mentioned earlier? How much is it worth? Right? We believe it's worth a lot.
Well, the other question is, how can software developers get part of that money?
How they what?
How can software developers get part of that money? Because if you save somebody else money, that's good for the world, but it's not necessarily going to finance software development.
Well, I can't solve all the social ills of the world.
Hi, thanks for the talk. Have you thought about using types, checking the types to improve the unsafe impedance? And if so, how?
Typed languages can help with this. That certainly is true. Int pointer is a type. And so...
Well, at least in C, it's appointed to a value of a particular type. And I'm thinking, is there some way of ensuring that at least the code, the unsafe code, is returning the types you expect? So that possibly dynamic typing?
And again, this is going to be a language implementation choice rather than what we are saying, which is this is the goal that we're attempting to achieve. If they are implementing the language, and as they are implementing the language, they decide to do typed or dynamically typed or those sorts of choices, if they make those types of choices, that can then lead to more unsafe impedance, and we could be better off. If they choose not to go that way, that would affect their rating in their unsafe impedance. We don't have a numeric calculation for it yet. We just have this sort of grouping at this point, but we're trying to get together a team to actually come up with a quantitative measurement of unsafe impedance.
Just an observation, I think all of the languages you thought had at least a reasonable degree of impedance were typed.
Yeah.
Hi Lee, thanks for the talk. In response to that conversation that was going on backwards and forwards, the OpenSSF is working on several sets of tooling and other types of things which I think are going to be used as instruments of torture for development process stuff. So it's nice to know that we can poke at the Rust thing, but I'm pretty sure that tooling's going to turn up that will lint the hell out of unsafe. And that will be a requirement for anybody writing Rust code that you've passed that linter, so that there's going to be a whole bunch of process stuff that gets applied to different areas to tighten up the laxness of some of their areas, right? And I think the inverse question that I have is what would we do to our tool chain? And I think your ideas of what you can load and when you can load it. So there is going to be a whole bunch of fingerprinting attached to code stuff. If you look at everything that's happening with SBOM and all these other types of things, that's going to start turning up in spades. So a lot of these things, I then think that they'll be throwing lots of money at AI to go look at any of the libraries which have the SBOM associated with it and think very hard about pointer offsets and whatever it is. So it doesn't make sure that they're going to fix it from a language purity perspective, but they're going to have people looking for the lots of things. So they're going to start boiling the frog at multiple ends in this particular area. Whether it actually gets them to where they want to be is unclear, because this is a highly complex space, but there are people thinking about a whole bunch of other things. And if you've not paid attention to what the OpenSSF is doing, I think that's where a bunch of solutions will be being driven through for all of these different languages, including ours. So if we're not paying attention to those types of things, I mean, we'll have problems in the future.
Along those lines, I had a really wacko idea. I like wacko ideas. I really do enjoy them. Wouldn't it be cool if any language like Rust or Swift or whichever they are that actually have this unsafe indicator in them so that unsafe code can't be hidden? Wouldn't it be really cool if any function or method or whatever it was that was hiding unsafe was required by the compiler to have unsafe in its declaration? And now what if that also went up to the library level or the application level? How many people here would use an application called Unsafe Word? You see, and now suddenly we've got social pressure to actually write safe code.
I think some of the recent security incidents were fixed on the level of open software, where volunteers were maintaining it. I'm rather curious to know how these people would be happy to fill in UAP forms, be incentivized, because they're not at all currently, and how we as a society just fit into, how can that be fit in? When we're using free software, but it is not free in some way.
So when we develop the quantitative measurement of unsafe, which is our next step, we hope that that will become a sales tag. Our library has an unsafe impedance of, okay? And that in and of itself would be something that developers would look at, not just that something is free. If you've got two libraries and one has a measured higher unsafe impedance and they accomplish the same thing, what is a developer going to pick? And eventually, all open source software is written with the hope that somebody's going to use it.
And we can talk offline if you want. So this is a very interesting topic. The EU CRA, as it was set up and designed, so nerddom related to the law, is that they want the end user software product has to have a CE mark associated with it. They're putting CE marks on software. There is no natural requirement that libraries underneath those things have CE marks on them, but I personally believe that one of the ways to generate the business that you're looking for is that you start putting CE marks on the underlying libraries. The advantage of that is that the business end-using customer should be forced by the regulators to prove that they can actually qualify their underlying code. And the smartest thing that the C-suite guys would want is to turn around and buy a CE mark from somebody on the outside. This can create a business environment where the C-suite actually wants to pay for support for open source projects because they're essentially outsourcing their liability. I haven't solved the problem yet, but I am talking to insurance folks and other people that would allow you to actually then have that CE mark, and you can create a business chain there where you're not charging for the intellectual property of the open source, but you're charging for the quality and maintenance of that open source over time. So I'm actually trying to fix that problem at the moment, but there's politics and people involved.
Any other quick questions? Time for one last.
Just a very down-to-earth question. What makes you put Java in the low impedance category? Is there any fundamental difference? I assume it's because of the native interface and because of some APIs, unofficial APIs like off-heap memory or things like that, which are unsafe. But this should be easy to disable, right, on the language level? Or is there something else?
So in the past, Java has been a little nasty to work with, but there were lots of tools created so that it would auto-generate your C headers and those sorts of things so that you could load stuff. A recent decision was made, a lot of work was done in the Java community, and the old way of executing native code is going away. And it's being replaced by a brand new methodology, which is built into the language itself. And all of their presentations on it discuss how they're trying to balance between ease of use and security, which right there tells you they're trying to make it as easy as possible to do horrible, nasty things.
Okay, so it's losing.
It's going down.
Okay.
Yeah. From what I can see in the sample code and those sorts of things that the Java community is putting out, the unsafe impedance appears to go down in this latest release.
Interesting. So getting closer to C#, maybe.
Yeah.
Okay.
Thank you for the great talk.
Thank you very much.